This is a lecture on calculating the shortest distance from a point to a plane. This is a point that's not in a plane, and it relates to the homework assignment concerning the person in the tree, 25 feet up in a tree, and a tarp underneath the tree. So here is the homework problem. You're in the tree at some point, x0, y3, and it's 25 feet in z, so you're 25 feet off the ground, and you have 5 feet of rope. Just a minute, let me get the highlighter here. So here's the point where you are in the tree, and you have 5 feet of rope, and you want to know if you can get down. You can assume how far you can jump or whatever. Anyway, work through the problem. At the base of the tree is this tarp, and it passes through the point 0, 0, 0. That's important information because you need a point in the plane of the tarp. Right. And here's the normal to the tarp, and from this can you calculate how far it is, what's the shortest distance from the tree down to the tarp. And there are two ways to look at this problem. So I'm going to do I'll do one way first with some numbers from a problem in Thomas, and then I'll show you how to do the other way. The first thing to understand is what is the shortest distance from a point down to a plane. Okay, and this is a figure from Stewart, and here's the plane shown in yellow, and it has a normal to it. Right, and remember that normal can move anywhere, but here's this normal vector attached to the plane, and of course because it's a normal vector it is at right angles to the plane. And here's the point in question. This is the location up here. Now you want to know this distance. This is the shortest distance down from this point to the plane. And you can construct a triangle like this. P0 is a known point in the plane. In the problem for the tarp, that known point was the origin, was 0, 0, 0, but somehow you've got to have one point in the plane that you know. And then you can construct this vector, B, I'm calling it B here, from the plane to the point. And I'll show later it does not matter which point you pick in the plane. That's interesting, but it doesn't matter. You could have picked a point over here or a point here. Doesn't matter. Okay, now you have this vector B, and you want to find the shortest distance. Well, you can see right now what it is. You see the triangle and the right triangle. So that distance is a dot product of B and N. It is a projection of B into the direction of the normal. Of course, you want to take the unit normal because you don't care. You just want that direction. So really you want the unit normal, although that's shown here as a normal. And then because normals could point in either direction, right, you could have this, the normal that's below the surface of the plane, you take the absolute value. There's your equation right there. So you need a vector from some point in the plane out to the point in question. You need the normal to the plane so you can construct the unit normal, and then you take the dot product. You project that vector onto the direction of the normal. Here's the problem that I'm going to work through. This is from Thomas, and although I usually like Thomas's diagrams, this is a little bit more confusing. Right. You could have done this in a different way. You could have taken this normal and located it someplace else and drawn a different vector so you could see the right angle that the normal makes with respect to the plane, but you don't have to. Here's the point in question, S. Here's the known point in the plane. Here's another known point, and I'll discuss that as we go along. Here's the vector, which we're going to call B, so it's a vector B, pointing from the plane out to this point. This is the normal, and from this we need the unit normal, so we just get the direction here. And the distance is the projection of B onto that unit normal, so it's the absolute value of B dot N. The first step, if given the normal, is to find the unit normal. You know how to find the unit normal. It's n dot n, and the square root of n dot n, and here it's the square root of 19. So here's the unit normal to the plane. There's an error that I've seen people make. I'm sure that you will never make it, but let's just do it again. If you have 3i, and then I have minus 2j, for example, say minus 6k, what's the magnitude? N dot n. So this is the square root of 3 squared plus a negative 2 squared. I have seen people take 2 squared and leave that negative sign. That's wrong. Again, it's plus a minus 6 squared. This is what it is not. This is just a review from algebra, I guess, but sometimes we make mistakes. It's not 3 squared minus 2 squared minus 6 squared. This is what it is not. So just watch signs and use parentheses. At any rate, at this point, we now have this unit normal, and we're going to use that in the problem. Now here's a big aside, but it's important for this problem, and it helps understand planes and the equation for planes and the normals a little bit better. When you have the normal to the plane, you do not have the equation for the points in the plane. The equation for the points in the plane is written from the dot product of the normal and any vector in the plane. Because the normal is normal to the plane, n dot any vector in the plane, which I'm calling r, is going to be 0. So how do you construct a vector in the plane? You have to have a known point, some reference point. You have to know that one. Okay, this is known to be in the plane. And then x, y, and z are just the coordinates of any point in the plane. So there's your vector r, x minus x naught in the I direction plus y minus y naught in the j direction plus z minus z naught in the k direction. X naught, y naught, and z naught are reference points. They will be numbers. Here is the diagram again of the equation I'm solving, or the distance equation I'm solving. Now look in this plane. There are two known points in the plane. One is this one, 0, 3, 0, and the other is 2, 0, 0. And over here, Thomas has written the equation for the line. Here was the normal, right? And n dot, a vector from any point, like any arbitrary point in the plane, x, y, z. Pen doesn't want to write. Okay. So here is the vector you would draw from this. You draw a vector out to here. We'll call that r. Vector's usually straight. Oh well. And then you would go n dot r equals 0 is your equation. You also could have drawn the vector from here to here, and you'll get exactly the same equation. N dot r tilde, in this case, equals 0. Both of these will give you this equation, and I'm going to demonstrate that. The trick is that you have to know that this is in the plane, and you have to know this is in the plane. So I'm going to do that calculation. Here you have that point that was named, 0, 3, 0. And here's the equation, n dot r equals 0. The normal dot any vector r in the plane is going to be 0. So the vector r will be x minus 0, because here's your 0, oops, here's your 0 here, and then it's y minus 3, and then it's z minus 0, and x, y, 0 will be the coordinates for any point in the plane. Work through this equation, and you get 3x plus 2y plus 6z, z equals 6. This is the equation for the points in the plane. Now I'm going to use the other unnamed point, which was 2, 0, 0. So I'm using the exact same equation, n dot r equals 0. I should have put an r tilde on there like I did in the diagram. So this is a little bit different r, but it's still in the plane. So we have the normal, 3i plus 2j plus 6k dotted with, and now it's x minus 2, using this, y minus 0, and z minus 0. Work through this, and you get exactly the same equation. Now I want to use that equation. I'm going to show you how to use that equation to determine if a point is in the plane. If I look at this diagram, well, I wonder if the origin is in the plane. It doesn't look like it is because it's in dotted lines instead of dashed, but we can figure it out. How do you figure it out? You put the coordinates of the point that you want to check, which in this case would be 0, 0, 0, into this equation, and you see if it works. So here's the question. Is the point 0, 0, 0 in this plane? So if 0, 0, 0, the origin, is in the plane, it would satisfy the equation for the plane. So I'm going to substitute x of 0, y of 0, z of 0 into this equation. Of course, it doesn't work. 0 is not equal to 6. Therefore, that origin is not in the plane of a plane with this particular normal. And the reference points that were given already. Okay, now we'll go back to solving the distance problem. So we're now looking for the shortest distance from this particular point down to this plane here. All right, we know this point is in the plane and this point is in the plane. I'm going to show you it doesn't matter which one you pick. But I need to construct a vector b going from the plane out to the point. I already have the unit normal. Okay. So here, again, repeated, the shortest distance d is a dot product between b, the vector from the plane out to the point, dotted with a unit normal, and the absolute value of that. So to get that vector to the point 1, 1, 3, I'm going to use the point in the plane 0, 3, 0 as shown in the diagram. So b, it would be, of course, 1 minus 0 for I in the I direction, 1 minus 3 in the j direction, plus 3 minus 0 in the k direction, giving me that vector b. When I take the dot product and work through it, I get 17 over the square root of 19. That's the distance. Now I'm going to do the same calculation using that other unnamed point in the plane to show you get the same answer. So here I'll use that unnamed point, 2, 0, 0, that was shown to be in the plane, construct that vector b. Right, there's my vector b, take the dot product of it with the unit normal, and I got exactly the same answer. Of course, that's no proof, that's just a demonstration. So in reference to that homework problem, you need to calculate the unit normal to the tarp. That's easy enough to do. Then you need to construct the unit vector, or the vector b, that goes from some point in the tree to the tarp. The origin, 0, 0, 0, is known to be in the tarp, so use that point. That will give you the vector b, and take the dot product of b and the unit normal, the absolute value if necessary, and that's your distance. Right, so just follow the steps as given before. Now there's another way to look at this problem. Okay, in this other way, you might say that if you have the rope in the tree, you can't really swing out and jump onto the tarp. Say you can only climb down the rope while it's hanging under gravity, and that way the rope would be hanging down the z-axis. Parallel to the z-axis, and that you were in the tree at the point x equals 0, y equals 3, and z was 25. So you need to find the z-coordinate of the tarp at these same values of x and y, and you'll see how far you are with the rope. To find that z-coordinate of the tarp, use the equation for the plane. 0, 0 is a reference point, and as before, you can create the equation for the plane of the tarp. And here's the equation. Use the unit normal, and x, y, z being any point in the plane. All right. Now, in this case, you know that x is 0 and y is 3 at the point you are up in the tree, and you want to look straight down and find the z-coordinate of the tarp, substitute that in, and you find the tarp is 2.5 feet off the ground. You're 25 feet off the ground. You have 5 feet of rope, and from that you can decide. In the other case, you find the shortest distance to the tarp, assuming that you could swing out. Then you've got to think about it. Can you swing out and get down?